Okay, hello class. Welcome back. And right now we're going to talk about section 7.4, which is the basic theory for systems of ODE. Okay, and we've been studying a little bit of linear algebra, and now we're going to connect that with our systems. So let me write our basic first order system as P11, which we've seen a couple of sections ago. We wrote it like this. And then P1n, the P's are all functions of T only. The xn's are our unknown function. And we think of the G's as the inhomogeneous term in each equation. Let's assume we have n unknowns and n equations. And when you do it this way, the way we're writing this system, it's in the form of a linear inhomogeneous, whoops, not G2, Gn of T. Okay, so it's the Pij's are of T are given functions. Gi of T is known. And so this is a first order. It's inhomogeneous if the G's aren't zero. So it's a first order inhomogeneous system. Let me get it to focus a little better. There we go. And our unknowns are the functions x1 up to xn of t. Okay, so those are the ones we want to solve for. Okay, and so the first, let's call this system asterisk with a circle around it. Okay, and the first thing we're going to do is we're going to write this system using what we know now about matrices. So asterisk star is equivalent to writing the matrix equation. Let's call this double asterisk star. Capital X prime of t is equal to P of t times X of t plus G of t, where X of t is the column vector x1 of t up to xn of t, containing all the unknown functions. P of t is the square matrix Pij of t. That should be a matrix. I've been writing matrices with square brackets. So this is Ij between 1 and n. And G is the column vector that contains all the inhomogeneous terms. So it goes G1 of t up to Gn of t. Okay, so just using matrix multiplication, you can see that this system is exactly the system we have written up at the top. Okay, and so usually when you have a first order equation, you have an initial condition. If you have n equations, you're going to need n initial conditions. So that means we're going to need an initial condition on each one of the functions x1 up to xn. So let's let me let capital X super 0 be x1 at t0 up to xn at t0. And so we let's look at the system we want to study. Oops, we want to study the matrix system double star with the initial conditions x of 0 is capital X at t0. And remember, that's equal to, basically, capital X is the matrix, the column vector x1 up to xn evaluated at, in this case, at t0. So you can even write your initial condition as a column vector, okay? All right, so that's how we're gonna actually, this can be very useful for us to study our system of equations by writing it in this kind of form. Now, before we do that, let's note something very basic about an equation like this. Suppose we look at, so let's consider the homogeneous system. Capital X prime of t is P of t, X of t. So let's call this triple asterisk. Okay. So theorem, and this will not surprise you based on what you already know. If x1 of t and x2 of t are two solutions of the system, the homogeneous system, then x1 multiplied by a constant plus x2 multiplied by a constant is also a solution of that homogeneous system. Okay. So in other words, in linear algebra terminology, a linear combination of two solutions is again a solution. Okay. So that's called the principle of superposition, which we have seen before. Okay. So that's not a shock. That's just basically an observation. Okay. And here's another thing which won't really surprise you based on what we already know. Now, the proofs of these theorems are, this one's easy to prove. We could do that, but I'm not going to do that right here. This next one is much more tedious to prove, although the proof is very similar to what we did in the case of second order equations. It's just now you have to work with n equations and n unknowns. And so this theorem is going to say that if you have, let's say we have x1 of t up to xn of t are linearly independent solutions of the homogeneous problem, which I call triple star, then any solution of triple star can be written let's say any solution, let me say phi of t of triple star can be written as a linear combination of these n solutions. Okay. In other words, if you know a little more linear algebra terminology, and I know a lot of you do, these xi, if you have n linearly independent solutions of a first order system of n equations, then those solutions form a basis for the solution space. That is, any solution can be written as a linear combination of those n linearly independent solutions. So in other words, what we're going to look for when we solve an nth order, a first order system of n equations, is we're going to look for n distinct solutions that are linearly independent. Then we can get all solutions that way. Okay. And so a set of linearly independent solutions is so special, we give it a name. A linearly independent set of solutions of a homogeneous equation of that form is called a fundamental set of solutions. Okay. All right. So we've actually heard that term before, and it's easy to see how this is just falls right into that case. Okay. All right. So basically, now the issue becomes when we have these solutions are going to look like row vectors. So question. How can we quickly, that's the question, or as quickly as possible, tell if a set of n solutions, if a set of n vectors, actually, it doesn't have to be solutions, but just a set of n vectors, say x1 up to xn of t, are linearly independent on some interval. Alpha beta. How can you quickly tell that? Okay. And the answer look at the Wronskian. Of these vectors. Now, first I have to tell you what that is. Okay, so what's the Wronskian going to be? The Wronskian is going to be formed by taking those vectors, and remember they were column vectors. So x1 of t up to xn of t are column vectors. In Rn. That means they have n components, okay, and there's n of them. The Wronskian of this set is, okay, we'll call it the Wronskian of x1 up to xn, and here's how you define it or make it. You take, remember, straight line means take the determinant of, and you put in each one of those column vectors as a column vector. So that's what I mean by squiggle. You copy the column vector, you put it in as a column vector, then you put in x2. And then you put in up to xn of t. Okay. Okay. All right. And if you think back to what we knew about the Wronskian for a second order equations, what did we know? That the Wronskian was for if you had solutions of a second order equation, the Wronskian was either identically zero, in which case they were linearly dependent solutions, or it was never zero, in which case they were linearly independent solutions. And you have a theorem that works almost exactly the same way here. So if x1 of t up to xn of t are solutions, not necessarily linearly independent, of our first order homogeneous matrix equation on some interval, let's say alpha to beta, then either the Wronskian of x1 up to xn of t is identically equal to 0 for all t in alpha beta, and therefore x1 up to xn is a linearly dependent set. So this is one possibility, or the other possibility is it's never 0. for all t in alpha beta. And, whoops, and therefore x1 up to xn. Whoops, no derivatives there. That's just an xn, x1 of t up to xn of t is a linearly independent set, okay, or a fundamental set because it's n solutions, they're all linearly independent, therefore it's a fundamental set. So you check, you have n solutions, okay, somehow you found them. Now do you know you have a fundamental set? Well, you have to check if the Wronskian is 0 or not. If the Wronskian is 0, you don't have a fundamental set. If the Wronskian is non-zero, you do have a fundamental set, okay? And then if you have a fundamental set, any solution can be written as a linear combination of those solutions you found already. So this is seeming a lot like what we had before, okay. All right, so let's, I don't know if you want to call it a note, let's call it a theorem. Another theorem we have is, again, if you look at x prime is equal to p of tx, and suppose x is actually a complex function, complex matrix valued function. So it can be written like this, where u, if it's a complex matrix valued function, it can be written as u plus iv, where u of t and v of t are real valued functions. Then u of t and v of t each must satisfy x prime is equal to p of t x, must satisfy the same differential equation, okay? So that was just like we had in the one-dimensional case, because remember we had complex valued functions that we were just thrown into when we look into second order constant coefficient equations. You could either write things in terms of e to the it with a constant, or you could write it in terms of sines and cosines. And those were the real value functions. And that's the same thing that goes on in these systems. We're going to see everything from the second order equations is really because you can write it as a first order system. And actually the nth order equations can be written as a first order system. We're going to learn that trick too in one of the last lectures. Okay. All right. And finally, this one looks a bit odd, but you'll see it in use and then it won't seem so odd. So the last theorem I'm going to quote is, let E1 up to En be the standard basis for Rn. Okay, so linear algebra people, you know what that means already. If you're not, that is E1, because I'm thinking of everything as every element of Rn as a column vector. So this will be 1, 0, 0, and there's n terms. E2 is the vector that goes 0, 1, 0, and then you keep going until you have n parts. And then you keep going until you get to En, which is the vector with all zeros, and then a 1 in the last slot. Okay. And suppose x1 of t up to xn of t are solutions of our homogeneous matrix system. Okay. On the interval from alpha to beta. And suppose we choose these the initial conditions for these so that xi at t0 is equal to ei. Okay, so that, and I'll show, you'll see when we work some of these out, this seems very odd right now to put that condition on. But in other words, you pick initial conditions so that you pick these solutions to satisfy initial conditions so that you put in 1, 0, 0, 0, and so on for the first solution as an initial condition. The second solution gets the initial condition 0, 1, 0, 0. Okay, so when you do that, then by doing so, you create a system, a set rather, of solutions that is a fundamental set. This was triple star. Okay, and we're going to want to be able to do a fundamental set of solutions of these equations. Okay, and basically, chapter 3 in this section, we're not going to do, I said this was section 7.3. This is section 7.4. I think I said that at the beginning. Anyway, I should have. We're not going to do any of the proofs in this section. They're way too complicated if you're not used to linear algebra notation. And we're going to, in the next section, we really begin to work with those first order systems, and you'll see hands-on how the problems go. And then this will not seem so strange. You'll see all the theory at work. Okay, so that's it for the lecture on section 7.4. And in the next section, we begin to study the systems of ODEs and put together all this linear algebra information we introduced in this early part of the chapter. Okay, see you next time. Bye.